All right, let's talk about factoring polynomials. And I know, the name itself can sound a little intimidating. But I want you to think about it differently. This isn't just about doing math problems. It's about building a toolbox, a mathematical toolbox, filled with these awesome techniques that let you take really complex problems and just break them down into simple, easy-to-solve pieces. So, let's get started.
Okay, imagine this. You're trying to figure out the area of a lawn, and the number you come up with is this expression, 60x squared minus 40x. I mean, it's technically correct, right? But it's kind of messy. It doesn't really tell you anything useful, like what's the shape of the lawn? What are its dimensions?
So that's the big question, isn't it? How can we take that expression and rewrite it into something that actually makes sense? Something that could, maybe tell us the length and the width of this lawn. Well, it turns out there's a way.
And the answer is factoring. That's the whole game. By using this process, we can transform that clunky 60x squared minus 40x into this, 20x times the quantity 3x minus 2. Now that looks a lot more like a length times a width, doesn't it? It's the exact same area, just presented in a much cleaner, much more useful way. So today, we're going to build the toolbox that lets you do exactly that.
Okay, the very first tool you should grab from your toolbox every single time, no exceptions, is the GCF. That stands for the greatest common factor. Seriously, whatever polynomial you're looking at, your first thought should always be, is there a GCF I can factor out? So what is a GCF exactly? Well, you know how the greatest common factor of, say, 16 and 20 is 4? It's the same idea, but for polynomials. It's the biggest, most comprehensive chunk, numbers and variables, that can divide evenly into every single term of your expression.
And the process is super systematic, which is nice. First, just look at the numbers out front. Then, look at the variables. And hey, here's a little pro tip for the variables. The GCF will always have the variable raised to its lowest power from the original expression. You combine those two parts, and bam, that's your GCF. Then you just pull it out front and see what's left behind.
Let's try it with this beast of an example. First, the numbers, 6, 45, and 21. What's the biggest number that goes into all three? That'd be 3. Okay, now for the variables. The lowest power of x is just x to the first, and the lowest power of y is just y. So our GCF is 3xy. We pull that out, and then we just divide each of the original terms by 3xy to see what's left inside the parentheses.
All right, time to add our next tool. After you've checked for a GCF, you might be looking at what's called a trinomial, an expression with 3 terms. You see these things everywhere in math, and honestly, factoring them is kind of like solving a fun little puzzle. So for the basic ones, the kind that start with just x squared, the puzzle is pretty simple. You're on the hunt for 2 magic numbers. These 2 numbers have to multiply to give you that last term, c, and at the same time, they have to add up to give you the number in the middle, b. Let's solve one right now. We've got x squared plus 2x minus 15. So we need 2 numbers that multiply to negative 15 and add up to a positive 2. Okay, let's test some pairs. How about 1 and negative 15? Nope, they add to negative 14. What about 3 and negative 5? They add to negative 2. Ooh, so close. We just need to flip the signs. Let's try negative 3 and plus 5. They multiply to negative 15, and they add to plus 2. That's it. We found them. So our solution is x minus 3 times x plus 5. But what if there's a number out front of that x squared term? Well, that just means we've leveled up to the advanced puzzle. And for this, we have a really powerful method in our toolbox, a special technique called factoring by grouping. Now, I know this looks like a lot of steps, but trust me, it's a super logical process. The whole trick is in step 1. Instead of looking for numbers that multiply to c, you're looking for numbers that multiply to a times c. Once you've got those, you use them to split the middle term into 2 pieces, and then the rest is just factoring in pairs. Let's just see it in action.
Okay, let's break this down. We have 5x squared plus 7x minus 6. So a is 5, c is negative 6. First step, multiply them. 5 times negative 6 is negative 30. Now for the puzzle. What 2 numbers multiply to negative 30 but add up to our middle number, 7? Let's think. Positive 10 and negative 3. Perfect. Now we use those to split the middle term. So 7x becomes negative 3x plus 10x. Now we've got 4 terms, so we group them into 2 pairs. From the first pair, 5x squared and negative 3x, we can pull out an x, leaving 5x minus 3. From the second pair, 10x and negative 6, we can pull out a positive 2, which also leaves 5x minus 3. And look at that! The 5x minus 3 is now a common factor. We pull that whole thing out to the front, and our final answer is 5x minus 3 times x plus 2.
Okay, so you've mastered the basics. Now we get to the really fun part. Let's talk about the power tools in our toolbox. These are special patterns that, if you can just train your eye to spot them, let you factor some of these polynomials in literally a single step.
The first and most common power tool you'll find is the difference of squares. Anytime you see a perfect square minus another perfect square, it factors instantly. It's just two sets of parentheses, one with a plus, one with a minus. So for 9x squared minus 25, well, that's just 3x squared minus 5 squared. So it becomes 3x plus 5 times 3x minus 5. Boom. Done.
Okay, quick but very important warning. A difference of squares, a squared minus b squared, is factorable. But a sum of squares, a squared plus b squared, is not. We call that a prime polynomial. It's a super common trap, so don't fall for it. Our next power tool is the perfect square trinomial. This is what you get when you take a binomial, like a plus b, and square it. The way to spot it is to check two things. Are the first and last terms perfect squares? And if they are, is the middle term equal to 2 times their square roots multiplied together?
Let's use it on this problem. The area of a statue base is 4x squared plus 12x plus 9. So, let's check. Is the first term a perfect square? Yep, 4x squared is just 2x squared. Is the last term a perfect square? Yes, 9 is 3 squared. And now the final check. Is the middle term 12x equal to 2 times 2x times 3? It is. So this whole thing factors instantly to 2x plus 3 squared. We just figured out the side length of the base. Okay, the last patterns in our toolbox are the sum and difference of cubes. Now, these formulas look a little scary, I know, but they follow a very, very predictable pattern. It's always a small piece, a binomial, followed by a longer piece, a trinomial. The real trick is just getting the signs right.
And luckily for us, there's a fantastic little trick for the signs. Just to remember the acronym SOAP. The first sign in your answer is the same as the problem. The second sign is the opposite of the problem. And the very last sign is always positive. If you just remember SOAP, you will never, ever mess up the signs on these.
So, we filled up our toolbox, right? We have the GCF, we have ways to handle trinomials, and we have our power tool patterns. But why? Why do we do all this? What does being good at factoring actually unlock for you in the long run?
Well, it turns out factoring is what we call a gateway skill. It's the key that lets you solve more complex equations. It's what lets you simplify those crazy-looking fractions with variables all over the place. It's how you find the most important points on a graph. It is absolutely foundational for higher-level math, for physics, for engineering, for so much.
And that really is the true power of this toolbox. Factoring isn't about memorizing rules. It's about a way of thinking. It's the ability to look at something that seems hopelessly complicated and break it down into its simple, understandable parts. It's about turning complexity into clarity. So the only real question left is, what problems are you going to solve with it?